Okay, well, thank you for the opportunity to make a presentation on a topic that I've been involved with for, wow, very many years, since some of the real early days of the story of long-chain polyunsaturates and infant feeding. I'm going to tell you a story that I partially developed in the context of a previous effort to look at nutritional requirements in prematurity that winds through the history of this area as an example of how nutrients become regarded as conditionally essential with the tools of modern science, which are a bit different than the way it was done in the 30s, 40s, and 50s, back when vitamins and minerals and other nutrients were being discovered. So here we go. Oh, and I want to thank the organizers for giving me a chance to present here. My conflict of interest slide here. I just have a few things to report. I'm going to tell you about the basics of omega-3 DHA, omega-6 arachidonic acid. ARA is the abbreviation which is used in the United States, AA in most of the rest of the world. Tell you a little bit about synthesis from precursors. Actually, that'll be more like towards the end. Tissue DHA data as well, human milk, a little bit about the balance of omega-3s and omega-6s, something about the clinical evidence, and something about arachidonic acid specifically because it is of high contemporary interest. This is a little bit of chemistry, the only chemistry that I think I'll show in this talk, and it's just to highlight the reasons why we call these fatty acids omega-3 and omega-6. And they have to do with the actual chemical structure. This is linoleic acid, and this is linolenic acid. And this omega nomenclature was developed in the 1960s by Ralph Holman in Minnesota. And he observed, and others had observed, it was well known at the time, that the position of the double bond as a chemical matter was six carbons in from the back of the molecule for the omega-6s and 3 carbons in for the omega-3s. And the reason that's significant is it's a back end of the molecule which actually imparts its essentiality to these molecules. So humans can't put double bonds in at this end of the molecule. And I don't have time to get into the biochemistry in this presentation, but it's becoming clearer and clearer with recent studies that it is this part of the molecule that makes these fatty acids essential. These are the longer chain polyunsaturates. So these are 18 carbon fatty acids. These are 20 and 22 carbon fatty acids. And we're going to focus mostly on arachidonic acid, which comes from linoleic acid, and then DHA, docosahexaenoic acid, which comes from linolenic acid, or alpha linolenic acid, I should say. And we can eat all of these molecules in our diets. However, the most prominent members of the diet are the 18 carbon fatty acids. And so what we'll be talking about is how evidence was developed to indicate and convince us that DHA especially and arachidonic acid should be in the diet specifically, and that we won't just be focusing on the essentiality of what is still called the essential fatty acids, linoleic and linolenic. Interesting, and this is the last I'll mention this, linoleic is probably essential for some skin functions, but not for much else. We don't know any functions that linolenic is actually essential for in terms of metabolic functions. We do know many functions that these molecules are essential for metabolically, and we also know that these molecules can go backwards if we feed only arachidonic EPA or DHA. Well, some of the earliest data suggesting that DHA and arachidonic acid were conditionally essential for infants comes from breast milk. And this is not a particularly early study. This is a study from 2007 that we were involved with. But I show it for in the interest of time rather than showing some of the early data, some of the 1980s and even 70s data. And what it shows is that DHA and arachidonic acid are in breast milks all over the world. So this is a meta-analysis of 64 studies involving 2,200 women, and DHA is in breast milks all over the world. The distribution is actually quite broad. Arachidonic acid is as well, and its distribution is a bit more restricted than DHA. But the point really is that both DHA and arachidonic are in breast milk. Now, one of the advantages we have in studies of infant feeding is we have a model of infant feeding. If you ask, for instance, what is the best nutrition for an adult of age 20 years, for instance, we can only speculate on what that might be. But for mammals, for human babies, for newborns, we have breast milk, and that can be a model that can tell us a lot about what is required for kids. And so, as I say, we find both of these molecules in breast milks worldwide, in all breast milks of normally nourished mothers. It's worthwhile reviewing a few principles of fatty acid nutrition, and as regards to tissue concentrations. So tissue fatty acid levels, as opposed to dietary fatty acid levels, I'm going to make a contrast between the two. Tissue fatty acid levels are maintained across broad ranges which appear to support normal function. And so we don't have very tight concentrations that only support certain functions. We really notice in most tissues broad ranges are sufficient. However, dietary fatty acid levels adjust all fatty acid levels in nearly all tissue to various degrees. When diet fails to support high or low thresholds, fatty acid metabolism kicks in, so synthesis and catabolism, that is the making of long-chain fatty acids, or short-chain could be, or their degradation, and that serves to adjust to maintain the levels that the tissue requires. So imagine that that you have broad ranges that are okay, but then as you get to levels which are too low or too high, metabolism kicks in and tries to push them back into a range which supports normal function. And so we have certain genes that we study. Our laboratory studies fatty acid desaturases and the elongation genes and their functions. This is the sterol-CoA that is less involved with polyunsaturated fatty acids. It's these guys that are most important. Those kick in, and then there's also beta oxidation that kicks in. But the key for our PUFA nutrition is to establish the diet high and low levels that support optimal function. So we might go too low, and we might go to zero. If we have zero DHA in the diet, is that okay if we have enough of the omega-3s, the precursor omega-3s? That's a question that we're going to try to answer over the course of this discussion. So I'm going to go back to some of the very early data that suggested to people that DHA is in fact required. And it starts, actually it really started in the 50s and 60s, but I'll start with a paper from 1976. While we recognize randomized trials in humans as the highest level of medical evidence for drugs and nutrients, we also recognize that the world out there, ecology, and our observations tell us something about how we would develop drugs, tell us something how we develop nutrients. So this is an example that comes from the early days where our colleague Michael Crawford, who is in London, analyzed 32 species of animals for their liver and brain DHA and arachidonic acid. And I've plotted them graphically here to show for DHA, I plotted them in order of increasing amounts of DHA in the liver, but those are the blue. But in the red is DHA in the brain. And what you see is that the DHA in the liver starts at very, very low levels for the zebra, for instance, and rises until you get up into much higher levels in what typically are carnivores like the cat, but not necessarily. There's a hamster right there. But they rise up to a certain level here. But you'll notice that even no matter what that liver level of DHA is, the brain level of DHA is relatively constant. It's relatively constant. It varies, instead of varying only from 0.4 to 0.32, it varies from to 32, I should say. It varies from 13 to 32. And so this was a first clue that DHA is conserved and may well be a limiting factor in the size of the brain that is attained by these various animals. The zebra has a very small brain. Same for the deer. Not so much for the elephant, but that's another story. With arachidonic acid, liver and brain arachidonic acid are show no such pattern. And so this really was one of the first pieces of data that told us that the rich level of DHA in the brain may well be very special. So composition is one thing, but what about function? You say, well, I've told you a couple of slides ago that tissue levels are maintained across broad ranges, but they're maintained to support function. Well, here we have one of the early studies, 1973, a functional study in the retina. Now, I want to point out that the retina, which is the light absorbing region of the eye, in the back of the eye, which is sky high in DHA. It's at 45% in some phospholipid groups, which constitute the majority of the membranes in the retina. In an experiment in animals, rats specifically, they were fed an omega-3 deficient diet in order to drive down that DHA level. And when they had that diet fed, the electrical response of the eye, and I should point down here, the electrical response of the retina was very much attenuated with respect to a light pulse. And I was about to say that the retina is thought of as the part of the brain that we can see. So it is a part of it is its own organ, of course, but it really is regarded as a part of the brain. It is connected directly to the brain through nerve fibers and transmits its signal to the brain. So these were some of the very first data, possibly the first data, that showed a connection between DHA levels and function. A little bit later, and of course I won't go year by year because that will take far too long. But in 1982, as an example of a study, this paper was in the American Journal of Clinical Nutrition. Susan Carlson, who's was a player in this area and still is since that time, looked at the fatty acid composition of infant red blood cells, and particularly their phospholipids, as a function of what they were being fed. And so in this column, there is human milk, and in these columns, there are formulas. And I'll draw your attention to DHA, 22,6, docosahexaenoic acid is 22,6. Now draw your attention here, and this is a human milk study, that the human milk level of DHA is actually higher in the erythrocytes of infants fed human milk is higher in DHA than those fed formula. So you see 6.8, 3.2, 3.9. And human milk again, as I showed you, has DHA, but the formulas of the day had no DHA. They had no DHA. So here is an example that gives us a clue that the tissue levels are actually dramatically lower when DHA is not specifically provided in the diet. The same was true for arachidonic acid. However, its reduction was not as large, and I'll have more to say about that later. There was a series of studies in the 1980s conducted by Bill Connor, the late Bill Connor, and Martha Nouriger was a major player on all this. Martha is still around. And these were dietary omega-3 deficiency studies that were conducted in infant rhesus monkeys. And they also were looking at visual function in these animals. They looked at many other things too, but visual function. These studies, to some degree, recapitulated the data that was found in rats that I showed you a few slides ago in 1973, but they conducted the studies in a different way. They ensured that the omega-6s were sufficient in those animals. And of course, they're able to look at tissue levels. So they were doing specific omega-3 deficiency. Now, these data in the top slide here, which I copied out of quite an old book, just simply demonstrate that there is a deficiency condition. And they also demonstrate that the omega-6 fatty acid that we call 22,5, it only has one less double bond than DHA, substitutes in both the retina and the brain for 22,6. So just one difference in double bond is actually the difference in the composition between the retina and the brain in these animals. And if you look at early times, you see that the difference in visual acuity, that is the ability to see down the eye chart, this is called Snellen acuity, but we at least in the US think about 20/20 vision as being good vision. So this is the same story. The higher is better on this scale. And what you see is that the deficient animals are consistently below the control animals. And they had another group in which they restored the omega-3s in the diet of the deficient animals. And you can also see that their vision then was restored to the controls. And this was really very powerful evidence that omega-3s are the key to visual acuity, to the visual function, but really also to brain function as well. And so now we're seeing a picture emerging here where we see omega-3 fatty acids, and particularly DHA, in the brain as a conserved molecule in the structure of the brain. So that DHA is not burned, but is in fact in the structure of the brain. And we have evidence now that the function of the brain is influenced by that concentration in a very specific way. I mean, this is about as small a difference. The difference between one double bond is about as small a difference as is imaginable, and it makes all the difference in the response here. Similar data were developed, and this is still back in the 80s, similar data were developed again with the omega-3 deficiency model in learning. So this happened to be two different rat strains, and these data showed that in the deficient animals, they learned slower and they performed more poorly on the brightness discrimination task when they were omega-3 deficient. I mean, realize that this is way back in 1987, and people are still kind of conducting studies that are along these lines. There are many studies. There are 70, 80, 90 studies of this type that show more or less the same thing, that learning and discrimination and mood and a whole bunch of other things are actually a problem neurologically in omega-3 deficiency. Back to humans, now we're in 1990, and this was a very early and very important study that, here it is up here, Ricardo Wawi is the first author, and then there was a group in Dallas, the Birches, Eileen Birch and David Birch, and I think David's on here. No, he's not, just Eileen, and Dennis Hoffman. And here, this was a study of visual maturation in humans. And in this study, this is again a similar kind of study where they're looking at the development of visual function in these kids, and they had a human milk group, and then they had a group with DHA, and it only had DHA and EPA. I showed you EPA before, but that's not considered to be the active component. This is DHA only. And you can see that with better vision being lower, so you can think of that as being a finer degree of resolution in the eye, visual acuity, that is. The human milk kids are have the lowest threshold, and then the kids who don't have any have any omega-3s at all, which is not a particularly great experiment that one would want to do these days, but it was still an open question back then, have the worst threshold. A little bit of omega-3 is good, but that's no DHA. And then this one is the DHA group, and the DHA group is really about the same as the human milk group. And you see similar things for these other parameters, which are drawn from the actual measurements that are made. So these were, again, more strong data indicating that DHA is in the diet is the key nutrient that supports visual acuity. One of the things I haven't said to this point is that in omega-3 deficiency, and there are omega-3 deficient kids here, but in omega-3 deficiency in animals, we have many, many, many studies which show that animals grow just fine on an omega-3 deficient diet. In other words, the typical measurement that folks make to get an idea about whether an animal is thriving in infancy, that is growth, gain of weight, is really not affected in omega-3 deficiency as long as there's omega-6 in the diet. So if we simply weigh a baby and plot that weight, we will see the weight go up, and we might think, okay, well, that's fine, this baby is doing fine. But we have to make specific measurements to understand whether the brain and vision, but let's call it all part of the same thing, whether neurodevelopment, neurocognitive development is actually also progressing properly and according to the optimal trajectory. And so that's been a point of considerable confusion in this field over the years. The baby is growing fine, but you haven't measured the key issue, which is the function and development of the neural system. And that requires more specific measurements. These are not simple measurements to make, I should say. Skilled people are required. Skilled persons using specialized equipment are required for this. More data from the early 90s. There were two sets of researchers who looked at the levels of DHA in the brains of autopsy specimens from human infants that were either breastfed or formula fed. Now, this slide also serves for me to re-emphasize that in the United States anyway, we did not have DHA in infant formulas until 2001, and I'll comment on that later. But in these studies, and this study happened to be in the UK, and I don't think that Europe got DHA until 95. But in these kids, breastfed kids had DHA in their diets, and this is the weight percent of DHA in the brain tissue, the cerebral cortex tissue of autopsy specimens from breastfed kids. All the other kids who were on other kinds of formulas were considerably lower. And this was another clue that DHA, which is in breast milk, as I showed you, but not in these formulas, that DHA in the feeds are required to maintain levels. Okay, so now I'll talk a little bit about this concept of whether we can make the DHA that we need. So back to a little bit of ecology, we we understand that there are various ecological niches. There are herbivores that after nursing, after weaning, I should say, consume only plants. Then there are carnivores that consume vast majority of what they consume are meat, and then humans are omnivores. We eat both, and we understand, and I'll remind you that carnivores have greater protein requirements. They can't make retinol from carnitine. From keratin. They require vitamin A, and they cannot make the long chain polyunsaturates. They don't have the genes, functional genes. They have genes, but they don't function anymore. And so the question that we were trying to answer is, are we closer to being a carnivore or closer to being an herbivore? If you say that we don't need arachidonic and DHA in the diet, then you're really saying that we are closer to being herbivores, or that we are herbivores in that sense. But are we moving more towards carnivores, or have we moved towards carnivores? So that's a question that we're looking to answer. I'll show you a couple of slides now that refer to the accumulation of DHA in the brain, and I've already told you that DHA doesn't get to the same levels in the brain if it is not in the diet. Here are data that show you the actual kinetics of DHA arriving in the brain. So this is another autopsy study, 1992, from the late great Manuela Martinez, and it shows the long chain omega-3s in the brain, DHA. Here's EPA, which we mentioned, and then here's an intermediate one called DPA. And the first thing you can see is that EPA and DPA, it's a function of time. Here's normal term birth. Here's 100 weeks, so that's 2 years, and those two are very low, whereas DHA rises dramatically. So that's term birth. We studied preterms. When I say we, I mean the whole field. There was a lot of talk back in the 80s and 90s, and a lot of thought that the preterms were particularly vulnerable because they were just on the upward curve here in the last trimester for accumulating DHA, but you can see that it rises rapidly all the way out to 2 years of age. We can then ask, where is it in the brain? Well, it turns out, and I'll just go through this very, very quickly. This is a study we did in non-human primates, but mapping it, the brains are very similar among all primates. And this DHA is actually rich throughout the brain. It's rich in the, or I should say the cerebral cortex is rich in DHA, but also the basal ganglia and the limbic system, buried deep within the brain, are rich in DHA. There are structures on the midbrain, the superior and inferior colliculus are among the highest in DHA. Same is true for arachidonic acid. The brain is rich in arachidonic acid as well. So both of these are required for the function of the neural system. This is another autopsy study, but instead of going for 2 years, it goes out to 90 years, or actually the highest, the most aged person in this study was age 88. And what you can see is that rapid rise around up to 2 years of age, but it keeps going up to about 18 years of age, 18 or 20, something like that. And then it stabilizes. And so we are putting on DHA long after our skull is mature, our brain is at its final weight. It just keeps going up, and then we get whatever DHA we're going to have, and then we maintain it. These, of course, were autopsy specimens, and they were taken in the late 1990s, and so this would almost be a cross section of individuals born throughout the 20th century, these being the earlier ones and these being the much more recent ones. I wanted to show you one slide, a pretty important one, a pretty important study published in the Lancet in 1998 on executive function or neurocognitive development in infants fed DHA or no DHA over over the first few months of life. Time is running out, so I won't go into too much detail in this study, but I will say a few things about it. So this is actually a very specialized test that tests the ability of a child to focus upon multiple tasks in order to achieve a goal. So in this test, I'll actually start at the end. The baby, who is actually 10 months old in these studies, wants to get a toy, but that toy is hidden behind a barrier. The barrier has to be removed by the baby. The baby then has to grab the cloth and pull the toy to herself, and then she has to uncover the toy in order to get the toy. So this is a task, really several tasks. They're all tasks that the child can accomplish very easily, but the child has to focus and remember what she's doing and get to the end to get to the goal. And in this study, which was of children that were either supplemented with DHA and arachidonic acid to 4 months of age or not, were then tested at 10 months of age. And in this test, it was shown that this executive function, and this is a bit complicated how you interpret this, but it was shown that the ability to finish this test successfully was related to whether DHA and arachidonic acid were provided in the diet up to 4 months of age. And this is a lasting effect out to 10 months of age. So this was, you could say, a test of intelligence or neurocognitive development. Problem solving is what it is. Very important piece of work. Well, it was the late 1990s when already in Europe DHA was available in infant formulas, and when I refer to that, I mean to say that already there were many people who believed there was a conditional essentiality. In the US, it didn't happen until 2001. And so the reviews that were written in that era were really quite important. Up to that point, there were something like a dozen. There's 11, there's 10 in this particular review. There's 14 in this particular review, which was a couple of years later, showing mostly positive effects on central nervous system and vision. Some negative effects on growth, but that more or less disappeared. There wasn't that much. There wasn't that much to that. But I would also point out, when people refer to these studies as being mixed, as they used to quite often, they didn't mean mixed in the sense of some studies being negative and some being positive. They meant some studies were neutral, that is, no effect, or positive. And so we weren't seeing negative effects. We were seeing either neutrality or positive effects. And here is yet another statement by Gibson and McCready, who are still active today, referring to randomized trials showing good evidence that preterm infants show a clear requirement for DHA for full visual and neural development. That is a statement that it is conditionally required. And then they also were doubtful about term infants, and that it continues to be a little bit controversial, but still most people, I think, are moving towards the idea that it is prudent to provide these in the diet. Let's see. I'm running out of time. This was a study of ours that, this was a study of ours, and this was a study of human infants. It's similar to some other things that I've shown you. It's also regards retinal function and the response of the retina to a light pulse. So that's an electroretinogram. In these studies, these were non-human primate studies. We were looking at premature animals. This was a premature group that had no DHA and arachidonic acid. This was a group that had DHA and arachidonic acid. And this was a difference in the initial electrical response to a light flash. And with DHA, and we also were able to correlate this with the actual composition of the retina, we showed that with DHA, you've got a more intense light response, a more intense electrical response to light. And then this is called an implicit time, and that's the time to response. So a shorter implicit time is better. And so you have a more intense response and a shorter time to response with long-chain polyunsaturates. That corresponds very nicely to the visual data that was generated by actually in several studies, and I've replotted this here. This is again the Snellen acuity, where 20/20 is the best, and it goes down. Down is good, up is bad. And these were, this is a series of studies that were summarized on this plot, and the visual acuity was measured at 1 year of age in all these kids, but then plotted as a function of the time that those children had DHA and arachidonic acid in their formula, or in human milk too. And you can see a clear linear trend that shows better acuity at 1 year of age when there is more DHA in the diet. So this is more of the same. This is yet another study which moves away from the formula story and moves into children that have been weaned. These kids were breastfed for 6 months, and then they were fed on baby foods that were supplemented with DHA or not from 6 months to 12 months. And these kids ate about 3/4 of a jar per day from 6 months to 12 months. And once again, when they come in at 6 months, there's no difference in the groups. And then by 9 months, that is 3 months on this baby food, there's a significant improvement in visual acuity. Again, down is good, finer degrees of vision. The vision could discern finer degrees of finer patterns. And then out to 12 months, it's all consistent. This was a randomized, double-blinded or double-masked study. This difference is actually quite large. It's about 1.5 lines down the eye chart. This, to me, was an extraordinary result when it came out, and it was very much a very little appreciated study that showed a great deal. Okay. This is a far too complicated slide for this end of this presentation, but I'm going to show you in a large sense. I put this on here to say a few words about the biosynthetic pathway, but more importantly, just the major thing that there is competition between the omega-6 and the omega-3s, and when there is a big imbalance between omega-6 and omega-3, we get suppression of the other side. And what we're usually worried about is omega-6 being high and omega-3 being low, but it could go the other way around. And that's actually part of the story with respect to including DHA in formulas and not having arachidonic acid. And so the reason that there is competition between the two is because they share enzymes. The enzymes operate on both sides. They operate on omega-6 and omega-3. They're common enzymes, but it doesn't just end here in the synthesis story. So even when you get to arachidonic acid and to DHA, which is down here, when you get to these guys, when they get incorporated into membranes and when they are made into signaling molecules, and DHA is made into signaling molecules also, you get also the same genes and enzymes that are used to make both. And so competition is important. So you hear about omega-3, omega-6 ratios a lot. This is kind of the origin of that. It's not kind of, it's exactly the origin of that the competition is for the enzymes, and a huge imbalance in favor of one or the other is not a good thing. So if we ask a question, why is arachidonic acid in formula? It all is traceable to a 1993 study by Susan Carlson, published in the Proceedings of the National Academy of Sciences, where she fed DHA EPA only to preemies, and she found a difference in growth. And that seemed to be related to arachidonic acid or arachidonic acid related growth. It's not clear that played out. This was a number of years later. A few studies, there are not very many. There's only about 3 studies that were ever done on cohorts in which people looked at DHA alone versus DHA plus arachidonic acid. But it seemed, though, that when you go to an actual trial in which you compare the two, you don't have those kinds of differences in growth. So the growth issue became a non-issue soon afterwards. But I've actually included one slide here on one study that was actually positive, and this was 2000. And this was a study of DHA plus arachidonic versus DHA alone. That would be the study you have to do in order to establish arachidonic acid requirements. And this was, again, a visual study. So this was actually a mental study. But in any case, arachidonic essentially made functioning superior in infants compared to DHA alone. And that's actually the key plot right there. I'm running out of time, so I'm just going over this very quickly. I'm going to skip these two slides, but I will tell you that those two slides were non-human primate studies that showed that arachidonic acid doesn't change very much when you put arachidonic acid in the diet. However, when one puts large amounts of DHA against arachidonic, DHA then attenuates arachidonic acid. And that's what those two slides actually show. So recently, there has been discussion in Europe over removing the requirement for arachidonic acid in formula. And I've been involved in this conversation a great deal since 2015 and wrote an extensive review a few years ago, which the title of which outlines my position on the matter. And Bert Koletzko and a large group, including myself, got together and published something early this year, which recommends arachidonic acid be provided along with DHA. So if you put DHA in formula, we should provide arachidonic as well. And then a few numbers here as specifics for how much ought to be there. And the core of the arguments in favor of this involve both the attenuation of arachidonic acid by high levels of DHA and a concern that we have not studied these diets to much of a degree at all. They are almost unprecedented diets. They certainly are close to unprecedented in randomized trials. And we don't find breast milk that has DHA and no arachidonic acid. As I said, arachidonic acid is quite preserved. So you can sort of look up those studies if you're interested, or I can certainly answer questions about them. This is more about competition. This is a very early study from 1963 that shows graphically how, at least in linoleic acid, as linoleic acid goes up in a diet, omega-3 goes down in the liver, and you can see DHA going down greatly. In the United States, we're out here someplace. We're at not quite, probably not 10% of calories, but we're probably close to it. And you can see if you drove down linoleic acid quite a bit, you'd actually get synthesis and incorporation. This is incorporation also of DHA into liver. And that plays out in kids. So this was a study we did in 2015. We're continuing on with some of this. These were kids with severe acute malnutrition in the African country of Malawi, and the ready-to-use therapeutic foods that were used at that time. Some of them had very high amounts of omega-6, and when you put the kids on them, you got a dramatic decrease in DHA, which had never been looked at, interestingly. When we reformulated it to balance the omega-3 and omega-6, the kids actually were able to synthesize enough DHA in order to stabilize their levels. In other words, their endogenous synthetic capabilities were sufficient to supply at least the basal DHA required for the brain. I think probably more DHA would be better, but this was most of it. So I'm going to leave you with this slide. Ralph Holman left us a number of years ago. Ralph, as I mentioned earlier, was responsible for the omega-3 nomenclature. And one of the very last scientific papers he published was in 1991 in the Proceedings of the National Academy of Sciences. He was at that time interested in pregnancy and lactation. And I draw from there a quote. This is ALA, so the omega-3 intake should be increased during pregnancy, lactation, and infancy, when requirements for omega-3 PUFA are highest during development of the central nervous system. which is rich in lipids containing high proportions of omega-3 PUFA. Really, it's rich in high proportions of DHA. A normal brain cannot be made without an adequate supply of omega-3 PUFA. I can substitute DHA for that. And there may be no later opportunity to repair the effects of an omega-3 fatty acid deficiency once the central nervous system is formed. And those are words from a very long time ago, 1991, which I think have really played out. And so I thank you for your attention, and I hope this little historical tour through the way that, through the data that compelled people to believe that omega-3s are important as at least conditionally essential nutrients was helpful.